Hey, what's up you guys? This is Adrian Garbasov. The best way to learn data science is to teach data science. So let's start our data science journey with a Titanic Kaggle project. Let's go!
Okay then, you should know what's a Kaggle. Kaggle is a website where you can compete with other data scientists for money or for free. And the Titanic project on Kaggle.com is the first project you can submit. You can try your data science superpower on it. And what is Titanic Kaggle project? Titanic Machine Learning from Disaster. It's a start project for all the data scientists that want to do it, in a practice. So it's a base Titanic problem. You need to classify who would live or who not from the Titanic disaster. So you can see it on the screen, all the description about the challenge. You can find it on the Kaggle.com. You'll see all the descriptions, and you'll see the data. We have a training data set, test data set, the description of this data set. You can find all the solutions or in the notebooks, on the notebooks section of the Titanic competition. And I'll tell you about the solution of one of the members of the data science of the Kaggle.com. It's the solution from this member. I found it very interesting. Manav Sehgal. It's would be the author of this data science solution. And let's go and find it, this notebook. So we'll do it in the Google Colab. Let's dive in to this notebook, Titanic Data Science Solution. I love Google Colabs because you can easily share all the you can easily share the notebook. That's why I love Google Colab. And let's go and dive in workflow stages. So first of all, it's a question of problem definition, acquire training and testing data, wrangle, prepare and clean the data, analyze different patterns of the data. Then we'll try to do the modeling, prediction, and solve the problem. We would visualize and report and present the problem solving steps. And we'll submit the results. So all the question and problem definition you can find on the Kaggle.com. It's the site where that I previously told you, where you can compete with other data scientists in this art of data science. So our workflow goals is classifying, correlating, converting, completing, correcting, creating, and charting. Okay, then. So let's import all the libraries: pandas, numpy, seaborn, matplotlib, with the magic matplotlib inline, sklearn, and all the models from the sklearn, like logistic regression, linear, SVC, random forest, k-neighbors, perceptron, SGD classifier, decision tree classifier. So first of all, we need to load the data. So we can load the data to the Google Colab by importing the files, or we can use the API from the Kaggle.com. So we'll do right now we'll do this with the API because we don't need to download it by hand, so we can do it by API. So we need to download the Kaggle JSON file. Then we need to use the Kaggle API. So when it's downloaded, we need to choose the Titanic competition and use pandas to read the CSV files. So let's describe the data, print the column values. Which column do we have? It's a passenger ID, survived, class, name, sex, age, siblings, part, ticket, fare, cabin, and port of embarkation. Let's see the data. So we have it in the train df. Oh, train, oops, train df hat. So that's how the data looks like, and test data. So that's how the test data looks like. The difference is we don't in the test data we don't know who survived or not. And let's see the shape of the data. Train div shape. It's 891 rows, and test shape, it's 418 rows. So we need to understand which features are categorical, which features are numerical. Let's look to the data. So we see which features right now is see which features are categorical, which features are numerical. And the mixed data types, which features may contain errors. So you see that none is age, cabin. Yep. So we can answer which features contain blank, null, or empty values. What are the data types for various features? Let's see it. It's integers, it's objects, float. And the same for the test data. What is the distribution of features? Let's see traindf.describe. So we can count rows. We can see the mean. For example, for the age, it's a numeric feature. The mean for the fare. So we have 891 row, or 40% of the actual number of passengers. For the train data, survived is a categorical feature, so we need to classify survive. If the passenger survived, it's 1, or if passenger is not survived, it's 0. Most passengers didn't travel with parents, so it's about siblings. Nearly 30% of the passengers had siblings. Fares varied from passenger to passenger, and few elder passengers within age range for 65-80. What is the distribution of we can see what is the distribution of the categorical features. The categorical features is name, sex, ticket, cabin, embarked. You can see the distributions. So I'll tell you about the results. Names are unique across the data set. You see this. Sex variable has two possible values. 65% are male. Cabin values have several duplicates across samples. Embark takes three possible values. Port of embarkation. Ticket feature has a high ratio of duplicate values. You can see this about the unique. Assumption based on the data analysis. You can see all the assumptions about correlations, completions, and correcting. What would we do next in creating features and classifying? I would not tell you the whole description because you can. I will attach the notebook and you can do it by your own. Okay. Let's start the pivoting and the analyze by pivoting features. We see right now the class of the passenger and the survived ratio, and by this we can do different conclusions. Okay. About the passenger class, we observe significant correlation among passenger class and people who survived. We confirmed that observation during problem definition that sex had very high survival rate. Okay, let's see this. You see that in the first class, high survival rate. In the female sex, high survival rate. What about ceilings? These features have zero correlation for certain values. It may be best to derive a feature or a set of features from these individual features. So we would mix it and make a feature engineering. So you see the correlation in ceilings, you see the correlation in parch. Okay, let's go next. Analyze by visualizing data. We'll use Seaborn library to analyze the distribution in age and survival. So we see the correlation, okay, and observations that infants had high survival rate, oldest passengers survived, a large number of 18-25 years old didn't survive. Most passengers are in 18-35 age range. You see the decisions. Let's see the correlation between numerical and ordinal features. We'll use the Seaborn library to see the correlation between passenger class, who survived, who not survived. It's a first passenger class, second passenger class, third passenger class, and the age distribution. You can see the observations, you can see the decisions. Would we use it in the model training or not? Correlating categorical features. Okay, let's go next. You see we use simple libraries, simple correlations. Here we see the correlation among the port of embarkation, survival rate, different port of embarkation, S, C, Q, male, and the sex, male or female. We see that in the most ports of embarkation, females correlation with the survival higher, so we would use it in the modeling too. Okay, let's go next and see the correlation between categorical and numerical features. So the fare, sex, and the port of embarkation. First, we did all the analysis of the data and the features of the data. So let's do the feature engineering. We collected assumptions and decisions regarding our data sets. And let's do the correcting by dropping features that are not correlating with the survival column. So this would be a good starting goal to execute. Based on our assumptions and decisions, we want to drop the cabin and ticket feature. So let's do it. And we see that before what we got before and after we dropped the columns. So let's create new features from existing features. So that's how our train data looks like. Passenger ID, survived, passenger class, name, sex, age, sibling, part, fare, and port of embarkation. We dropped features that are not correlating with a survived column with our target. For our train and test data set, we can extract the title from name. So we see for female and male, we can extract the title of a passenger and use it as a feature in our model. We can replace the titles with a more common name or classify them as rare. We would do it with a for loop and with a replace function. And we see the correlating between the title and the survival. So we can convert the categorical status to ordinal. We don't want to use Mr., Miss, Mrs. We want to do it. I want to do it to use our. We want to use in our model numerical columns. We can do it by converting categorical types to ordinal, or usually we can do it with a one-hot encoding. Now we can safely drop the name because we can't use this in our model. Besides of it, we would use the title. Okay, so let's work with our categorical feature and one hot encode male and female. Now let's do something with missing values. We can drop it, or we can generate random numbers between mean and standard deviation, or we can, more accurate way of guessing missing values is to use other correlated features and see the correlation between different groups of missing values. Or we can combine all the methods and instead of guessing, use random numbers between mean and standard deviation for different combinations. So we can see the using Seaborn library for correlating features with the missing values. We can prepare different classes of guesses for missing values. Now we iterate over sex and passenger class to calculate guessed values of age for the 6 combinations that are missing. We're doing it with a for loop. We're using median function and we convert random age float to nearest age, and then we allocate missing values and put our guesses in missing values. So right now we don't have missing values, but we with the next step we can create bands for different not categorical but for different ages, because it can better correlate with our target. So we see the different correlation with the survive target of different age bands, and we can we can make the new feature depends on the age band it has. And we can replace age with ordinals based on these bands, because these bands got better correlation, and in the, for example, in linear models, it would get better result for training and testing error and accuracy rate. So right now, as we have age bands, we can replace the age band feature with numeric. And based on this, we can create different ages on age bands. Let's do the same for family size. We can see the family size and the correlation between the survive target. And we can create another feature called is alone or not, because we see if the passenger is not alone, it's better survived. Okay, then. So if it's alone or not, and we see the correlation between the features and the target. So let us drop part, sibling, and family size features in favor of is alone or not. So that's how our training data set looks like right now. And we can create an artificial feature combining passenger class and age. By multiplying the age and the passenger class. completing a categorical feature. So we need to do something with the port of embarkation. We would fill missing values with a for loop with a most frequent port of embarkation. It's S. Right now, we would convert categorical feature to numeric. It means the port of embarkation. We would one hot encode to numeric features. We are right now filling the fare with median values, missing the missing values. We are filling with the median values. And we would do the same with the fare. We would do the bands and make the new feature depends on the correlation of the fare band and the survival target. So that's how our training data looks like when we fill the fare with our fare bands, and the same for the test data. So now we are ready to do the modeling part and to see the accuracy and depends on different models on our training data set. The models would be logistic regression, k-nearest neighbors, SVM, it means support vector machines, naive Bayes classifier, decision tree, random forest, perceptron, artificial neural network, and relevance vector machine. So first of all, let's divide our training data set to training and target, X train, Y train, and do the same with test data set. So let's do it. And let's see the shape. It's 891 and 418. Let's start with the linear models, logistic regression, and see the accuracy rate for the logistic regression. It's 18%. The logistic regression is a linear model, and it's useful to see the correlation between different features and the target. So we can do it. You can see the code, and here is the different features and the correlation. Yeah. So the sex is correlated, as we saw previously, with a survival ratio, with a survival target. Then correlation is passenger class. The second feature, the title, because it's almost correlated with the sex, right? The our mixed feature, engineered age multiplied by class. So we can next we can use different model, the SVM machines. Let's see the accuracy rate. We can use k-nearest neighbors. See the accuracy rate. It's simple models, okay? It's k-nearest neighbors classifier. We can where we use 3 nearest neighbors, fit, predict, and the accuracy score. Naive Bayes machines, just the same, fit, predict, accuracy. Perceptron, linear SVC, stochastic gradient descent. Let's go next and use different types of models. It's trees, decision trees. We see high accuracy rate. It's even better than other models for this task. And decision tree is a simple model. The next model would be random forest. It's one of the most popular models for classifying. We would use it with 100 leaves, 100 decision trees, no cut at all. So we would see the accuracy rate. It's like the same because we got a little data. Do you remember that we got even less rows and examples than in our usual machine learning problems. So let's see how different models and the accuracy rate. So we see that the random forest and decision trees are the best for this machine learning problem. Then k-nearest neighbors, the logistic regression, stochastic gradient descent, and other models. And then we can submit our predictions. But I would so it's a machine learning. It was a machine learning models. So you see, you saw all the stages of machine learning project of machine learning execution. Let's do a little deep learning with Keras. Let's then do the same problem. Not we wouldn't do the feature engineering, but we would we would build the deep learning model on our data. So we would import Keras and all the Keras library and all the functions from the Keras library, TensorFlow, and we would make a train test split. So we would train our deep learning model on the train data and validate it on the test data. Okay. So we're doing the. Let's import the Keras. Okay. Let's split the data. And prepare the data for our model, neural network model. So it would be the sequential model with a dense layer, ReLU activation function with 8 units, 4 units, dropout, dense at the end, and the optimizer loss function, and the metrics would be accuracy rate. Okay, let's optimizer, let's do the callbacks. We would show you the callbacks every n epochs. So here you see that it would be Atom optimizer and the loss would be He uniform. Our neural network model. Yep. So let's fit it with 64 batch size, 1000 epochs, validation data from our train test split, 0 verbosity, and our callbacks. Okay. Right now we'll see the summary of our neural network model. So it's got 8 neurons on the first layer, 8 neurons on the second layer, 4 neurons on the third layer as a dropout, and 1 neuron on the fourth layer. So it's a small model with 185 params. And every 100 steps, we would see the average loss for the epoch. So our model is getting better. The accuracy rate for train data and the accuracy rate for the validation data. So our losses got better each step. We see that for the neural network we got a little data, it's like less than 1000, but it's a pretty good model, and it's not better than a decision tree, but it's not bad. So we can see our history, the shape of course we got 1000 epochs, and we'll see we would plot the history. So we see the loss function for the train and test data, and we can see the plot for the accuracy rate. So it's getting higher, and it's not bad for the train data, but it's not so good for the test data. So that was a neural network model. You can compare the accuracy rate with the models that we've done before. That was the Titanic challenge on the Kaggle.com. So if you like my code review, push the like button, subscribe. See you later.